Hello, I'm Mr. McBrien. This is TIJ1O, Circuit Schematics. Yesterday we talked a little bit about Ohm's law and some definitions with regards to electricity. Today what I'd like to do is back up a little bit. We've seen schematics that others have created. We've even talked about them. Now we can learn how to create our own schematics that match the way that electrical engineers expect to see schematics be built. Okay, so a little bit of background. When we design a circuit, there's a challenge with regards to communicating this. It's a critical part of design. Usually we design things in a community, so we have a team that works on things. We need to be able to talk back and forth, and sometimes that team will be not in the same room, right? Text-based communication really isn't effective when you're talking about two-dimensional or even three-dimensional systems. We need to be able to use pictures to communicate circuits. Okay, and like with documents, like with essays that we write, like with websites we design, there are accepted systems that make it easier for other people to look at what we have proposed and understand what we're saying. Good schematics are really pretty important. You'll see schematics being a major part of any patent document. We need to communicate with our coworkers what we want them to build or what we are proposing we build. When they build them, because often it's not the designer who builds it, we want our prototypes to be accurate. We want them to work with as little trouble as possible. So we don't want to cost ourselves patents. We don't want to cause miscommunication with workers and delay projects. At best, a bad schematic is going to be inconvenient. At worst, it could be, in fact, quite dangerous. Okay, well, we've talked about circuits, and we implied several things. First off, lines, they represent wires. No great shock. Dots actually represent soldering joints between two different wires. Now, intersections between lines in our pictures are not connections. They're not necessarily connections. The only time they're connections are when it's the only option available to the electron. So how do I illustrate this? Well, if we look at the corners of our schematic here, and this is one I've used several times already in this class, if we look in the corners, well, those are intersections, right? Yes, they are. And they don't have dots in them to represent soldering joints. This is fine. We know that these are connections, and the reason we know is because without them, there'd be no circuit. That's the only potential path for the electrons to follow. Now, in contrast, we can take a more complicated circuit like this one, and if we look at it, we can see in the bottom right-hand corner right here, we can see an intersection where there are many potential paths for the electrons to follow. So in that case, that is not a connection. So this is not an intersection between four wires because there's no dot there. Instead, what's happening is two wires are crossing each other in order to be able to build a bigger circuit, be part of a bigger circuit. Sometimes you'll see a little, almost like a U that shows a ramp going one wire over the other, but it's often not convenient to do that. And so we have to be able to interpret this piece. So we can see there are lots of places where we do have intersections of more than two wires, and there's a dot to tell us that this is a soldered joint. And in this case, no dot means this wire goes over top of this wire without them connecting. I hope that's clear. Alright, we've already covered a bunch of the symbols. Here are some more, and I printed up a sheet for you to include in your notes. You're responsible for all of these symbols, even though we won't use a capacitor in this classroom, and we probably won't use a transistor either. but you're responsible for these. I'd focus your attention on especially this LED, this light emitting diode symbol here. It's a diode with two arrows representing light. I'd focus your attention on this switch, the ground, and the resistor as the most important ones. Oh, and of course our power supply, which we covered yesterday. Okay, a little bit of reminder about the power supply. So it's the source of potential. It's the push for electrons through our circuit. Usually it's direct current in our classroom. Almost always when we discuss, we'll talk about direct current. And if it's a single cell battery like a AA or a AAA battery, it's 1.5 volts implied. So sometimes we won't say it. We'll just draw a single cell and we'll assume it's 1.5 volts. But usually the voltage is written beside the symbol for the battery. Now batteries are directional, right? They push electrons in a specific direction. So the schematic has to show which direction the battery needs to be connected up. Our coworkers need to know which way to connect the battery. So the larger bar on the symbol that we'll see in a second is the positive terminal of the battery. So right here we've got our larger bar. That's the positive terminal of our battery. We can label the power source in a lot of ways. We can just say VCC. We can write a positive voltage in place. We can label it hot or talk about it as the hot on the system. The convention when you're building a circuit is to use a red wire. We'll often use orange as a stand-in for red. I'll explain why in a bit. But red wires denote positive voltage. Now, in general, when you see a circuit on a page, the positive potential will be at the top of the circuit. So in this case, we can see our red wire here showing the positive. So we can think of this as there are at least three clues as to where the positive is on here. The larger bar on the power supply, the red wire, which is fairly uncommon, but it's very common when you're building the circuit. And it's the top of the circuit, where we generally put power. Okay, so now if we have a positive potential, we also need a negative potential. So the ground is the source of electrons. It's 0 volts, and it's the negative terminal on the battery. When we look at the battery symbol, it'll be the smaller pole of that battery symbol. But sometimes a circuit designer will just communicate that it's grounded by using the symbol for a ground. If you see this, it still needs to be connected up to the negative terminal of the battery. Okay, and to illustrate this point one more time, here's our classic circuit that I've been using all the way through. Here's an alternative. Now you can see the negative portion is the bottom of our circuit. It's also shown by the smaller pole on our battery symbol. So this is pretty clear what this circuit is. This is an identical drawing. Okay? The LED goes down to ground, just like the battery does. So this is an equivalent drawing. These two are absolutely the same. It should be interpreted the same way. And like I said, the ground is at the bottom of the circuit, typically, when possible. So I alluded to wires at the beginning. Lines on the schematic, of course, represent wires. Schematics, whenever possible, have wires drawn vertically and horizontally. So back to our classic case, right? You notice these lines are straight and they're up and down. So that is an acceptably drawn circuit. This, on the other hand, roughly at 45 degrees, is not an acceptably drawn circuit. In general, they should be vertical and horizontal, all the wires, wherever possible. Current flow, we alluded to this yesterday. The direction of current flow is from positive to negative. And another way of saying that is from source to ground. Now, in any simple circuit, and we'll probably do some definitions, well, maybe tomorrow we'll do some definitions of what a simple circuit is, but a simple circuit has only one direction for current to flow, right? And in that case, in any simple circuit, then the current flow is the same across any point in the circuit. Remember that the electrons need to return to the battery after they flow through the circuit and give their power to whatever load is there. So the current, then, is the electrons per second. And so it has to be the same at any point in the circuit, or the electrons would they would accumulate. And this doesn't happen in a simple circuit. Okay, so remember that the direction of current flow is the opposite direction of electron flow. We generally draw arrows to show the current, okay? And so that means it's from positive to negative. And incidentally, make sure that your diodes point in the direction of current flow. See how they're an arrow? They're pointing in the direction of current flow. Okay, when you're drawing circuits in TIJ, many of you are motivated by marks. Nothing wrong with that. The way to maximize your marks, do your best to practice drawing the circuit symbols as clearly as you can. Try to match what's on the diagram. Try to be as tidy as you can. And be sure to use a straight edge for wires. So there will always be a half a mark for using straight lines. If you want to use your calculator or whatever, that's fine. You don't necessarily have to use a ruler, but be sure to use a straight edge for the wires. And to be clear, in any material that you submit for evaluation, an aspect of it will be neatness and accuracy. And this is simply because you're trying to communicate with your coworkers, and accuracy is a big deal. Neatness helps you to communicate well. So some of you might be curious about things about, does the power always have to be at the top? Do wires always have to be vertical and horizontal? And the question would be, is the schematic wrong if it breaks those rules? Right? And the answer is no, it's not necessarily wrong. These are guidelines, most of them, and they help reviewers look at schematics very quickly and get what they need to out of it. If you don't follow those guidelines, there may be issues with that, but it doesn't make a circuit necessarily wrong. And in some cases, with very complicated circuits, you'll need to break certain of the rules. You might have to, for example, have a diagonal wire for some reason. There may be times when it's necessary. It won't likely be in our class because we won't be building such complicated circuits. When there isn't a significant reason to break from the convention, just follow the guidelines we've seen and you'll do fine. Okay, for your homework, please complete the circuit schematic worksheet. Make sure you bring in the safety sheets because we're going to start working with electricity tomorrow. All right, good enough. Thanks, and have a great day.